Okay, so what we're going to be talking about today is relating the canonical partition function to other thermodynamic functions. So today, we're going to go Q, we're going to calculate S, P, A, and mu, I think, chemical potential. So far, we have calculated Q going to U, where U, pardon me, So the first step is we're going to go through, we're going to manipulate the partition function in a generalized form using kind of a relationship between classical and stat mech. And then we'll go through and we'll calculate all of these parameters for an ideal gas to tie it back in so we can see the whole procedure. Okay, so the starting point is going to be very similar to what we've done previously with classical thermo. So we're going to expand the natural log of the partition function, which is the important sort of mathematical function that we've been manipulating so far, with respect to T and V. So we're relying again on the Gibbs phase rule, where we're saying we only have to specify two variables. So that's why on the left-hand side we have the total differential, because we're keeping track of all of the different possible ways that the natural log of the partition function can change, because we're saying that there's only two functions or two variables that are changing due to the Gibbs phase rule. So we multiply both sides by kt squared. So ultimately what our goal is trying to be is to get the partition function dlnq into some form that looks like in a form like this. Right, because if you recall, this is the combined first and second law of thermodynamics. So this equation is always valid under all circumstances. No assumptions necessary. So what we need to do now is to translate between ds and dt, and rather du here as well. Right, so we have to do a little bit of manipulating with thermodynamics to swap out the dependent and independent variables to get into this form for the simplest form of the combined first and second law of thermodynamics, which is going to be our easiest gateway into things. Okay, so I'm going to call this we're going to come back to this term right here, this function right here, or equation I'm going to call A. So the first manipulation and again, these are relationships that are kind of derived after lots of trials and errors, so it seems very convenient working through it this way. Now we can rationally kind of think about why we'd want to look at u over t, because if you remember, 1 over t is defined as ds d. Did I get this right as reciprocal? Is that right? Or ds du? I'm trying to draw a blank here. No, this is correct. So you can see here that if we move the du over to this side, du over t equal to ds. So this is fitting into our goal of getting things into this tds minus pdv form. So we rearrange the expression. I'll call this B. So we'll put equation B into equation A from the previous slide. Okay, we're going to try and rearrange it. Remember, this is our goal. So we're getting close. We're almost there. So if we just do a little bit of rearranging. We'll combine these differentials here. I'll just go to the next slide so I can write out the final form. All we're doing in this last step here is just substituting in the partition function for the u over t term. Oops, d here. So we have met our goal. So the simplest one to put together is that P is equal to the Boltzmann constant times by the temperature and the partial of the partition function with respect to the volume. With the entropy, just requires a teeny little bit of manipulation. I think this is the first theorem of calculus, is that what it is? Where you take the integral of a derivative, right? It just kind of cancels out nicely. Which means that S is equal to plus some constant, but we know that the constant is 0 because of the third law of thermodynamics. So we have an equation for entropy based on the partition function. Okay. Helmholtz is defined as U minus Ts. So this term here is the U. Those two terms cancel out, and the Helmholtz energy is a nice, convenient function. So the canonical partition function is the most simply and easily related to the Helmholtz free energy because it shares the same thermodynamic variables, fundamental thermodynamic variables. Right, so just in the same way as with classical thermo, you can calculate any function you want from any sort of starting point, but there are some functions that are much easier to calculate based on having particular variables held constant. So in this case, in an NVT system, Helmholtz is easiest to calculate. NPT, Gibbs free energy is easiest to calculate. So in this case here, the free energy of the system is directly related just to the number of states that you have in the system itself. Now for different partition functions, this is going to be a different relationship. So in what they call the microcanonical partition function, typically we call it microcanonical, This particular one here, we draw it as a capital omega, which is the degeneracy, and this is an NVE system. In this case here, entropy is its most base unit. That's the partition function we'll be talking about on Wednesday. And with this relationship from Helmholtz, we can actually draw connections back to what we already derived. We have thermodynamic identities where dA, the change in Helmholtz with respect to volume changes, is equal to minus pressure. And so if we take a look at this form here, minus kB T ln of Q, we go back to our pressure term, it is simply just taking the partial derivative of that with respect to volume. Same thing applies if we look at dA dt, change in Helmholtz with respect to temperature at constant volume. This is equal to, minus pressure, and minus entropy. Same thing, we go back and take a look. It's exactly what we have. We also have to do the product rule, right? We have the two terms there and there. So I like the approach of the Sandler Stat Mech book because it jumps back and forth between the classical and the statistical world, which makes it so we don't have to be in the weeds sort of with Stat Mech quite so much. We can rely on expressions that we're already comfortable with. So lastly, we can write the chemical potential with respect to Helmholtz energy. In this case here, the chemical potential is at constant T, V, and Nj not equal to I. We're more used to the chemical potential being related to the partial Gibbs, but we typically do NPT. So in this case, the chemical potential using the canonical partition function is just given by this expression. And from here we can go on. As an example, if we want to crunch the numbers, we can calculate the enthalpy using the canonical partition function, right, which is U plus PV, internal energy, plus the PV expansion work. And if we write this out, N and V. Not really the easiest function. Yes, we can. We can calculate the enthalpy if we wanted to. But if that's the parameter that we were most interested in, we should probably be working in a different partition function to make things more convenient. And we can keep going on and on and on with different thermodynamic variables. Okay. So let's go back to the ideal monatomic gas. Yes. Sure.
What's the second term, the partial?
It should be N. It looks like a W. I just scribbled badly. N. There it is. Yeah, so most of this expression here, this and that term is the pressure, and then that's the P times V. And we're calling the canonical partition, or the canonical ensemble, right, we're fixing the volume as a constant. So we can add that in there. Okay, so this can serve as a recap of what we were talking about last week and also transition us into calculating more parameters than just the internal energy. So the energy of a particular state is going to be the energy of the translational energy states. We've talked about this a little bit, but we can potentially have electronic energy states. How excited are our electrons? And you can also have different energy states of the nucleus, right? They're still quantum mechanical particles. So the partition function for a single particle, which is given by the lowercase q, is the summation over all of the states I, scaled by the Boltzmann factor. Now, if we make the assumption that each of these energy modes are completely independent, right? My translational energy state can be completely independent to my electronic energy states. Then we can break this partition up into individual partition functions. We write this as the partition function of all the translational states, the partition function of all the electronic states, and the partition function of all the nuclear states. We had already found that we can write the translational partition function like such. And to simplify the expression, for most calculations that we'll be worrying about, unless you're at a, yeah, question?
So, we for to write out that they're the products, we have to assume that they're independent because it's already built into the form of the function.
Correct. So, transitioning from this form here to this form here, we have to assume that the translational, electronic, and nuclear functions are not dependent on one another. So we could write out the translational function as summation of e to the minus beta epsilon translational energy states. The electronic one is summation of e to the minus beta energy of the electronic states, and same thing for here. Now, when we're transitioning from an ideal gas to a non-ideal gas, we won't be able to make this assumption anymore. When you have interacting gas particles, the energy of a gas molecule is going to be dependent on the locations of the molecules surrounding it. So these multiple energy modes is not going to be possible when you have a dense fluid. Multiple independent energy modes, rather, is not going to be possible when you have a dense fluid. But for now, we're looking at the internal structure. Now, this may not be strictly 100% true, but for simplicity of the calculations, we're going to assume that they're independent energy modes. But if you have a large complex molecule, it may not necessarily be true that one vibrational mode is different from another vibrational mode, right? But if you're a molecule translating through a vacuum, well, the translation probably doesn't affect the vibrations, right? Because there's no drag at the atomistic length scale. It's not like there's like a wind, a molecular wind that it's feeling as it goes by. So the molecule doesn't matter how quickly it's going. So its vibrational modes should probably be independent. So for this here, this is a pretty good assumption. But the complexity of interacting gases is that we can't do this approach here. When you have interacting gases, the energy of the state is highly dependent on the energy of all the other molecules. So we can't do these just sort of combinatorial statistics and say, oh, q to the n over n factorial is the ensemble partition function. It gets much more complex. So going back to the electronic and nuclear states, if we say that the energy of sort of one step up for an electronic energy state is much, much greater than the energy involved in a translational energy mode. Right? That means that in order for us to get to these really high translational energy modes, we'd have to be at really, really, really high temperatures or something like that. So in general then, what we'll be saying is that E to the minus beta E trans, oops, not electronic, right? The Boltzmann factor for the electronic energy states is going to be approximately equal to E to the 0, which is going to be equal to 1. Right? Because if this term is very, very large, that means you have a large negative exponent. So that basically means that your electronic energy states, there's only one that is accessible at a reasonable system condition. So if we were to draw this out a little bit differently, and the same logic will apply here for the nuclear energy modes. Like so. So if we were to sketch this out a little bit, kind of similar to the example that we did last week on StatMech. If we had the energy of some state, and we were looking at the translational modes, the electronic modes, and the nuclear modes, we would have tons of different states at the translational mode. You maybe have a ground state for electronic, and then a really high one. And a ground state for nuclear, and a really high one. And this translational one, right, you're going to have all these states going all the way up and up and up and up and up and up. So remember, the partition function is the summation of all of the different states. But since this gap is so very, very large, almost all the particles are going to be occupying the lowest energy states. So when we're combining the probabilities of the particle having that particular translational mode and a particular nuclear mode and a particular electronic mode, the partition functions for these two are going to equal 1. Because in general, they're going to be only in one particular energy state, because the step-ups are much, much higher energy, so we're going to neglect them for our calculations. Now, if you wanted to repeat the calculations for extreme conditions of really high temperatures or something like that, then maybe you would have to include the electronic energy states. One additional note is that if you look at the heat capacity for particles as a function of temperature, it'll always tend to increase. They always kind of look like this. The reason why heat capacity tends to increase as you increase the temperature is because as you increase the temperature, you access these higher energy modes. But at low temperatures, there's only a certain number of ways that your particles can store energy, right? Namely, it's translation. That's the easiest way it can store energy. In a more complex molecule, rotation, fairly easy way to store energy. But vibrations between molecules and electronic energy states, those are really only activated at very high temperatures. So your heat capacity is going to continue to increase as you get access to more and more different energy modes. Okay. So now, our goal then is we want to calculate the partition function for a collection of gas molecules. This is an ideal gas, which means they're non-interacting, which means that the energy mode of any particular molecule is independent to the energy modes of all the other molecules in the surroundings. In interacting systems, that's not the case, right? Because you have energy stored up in the interparticle interactions. So you have to keep track of other particles, and they're not independent anymore. But if you recall, when we combine independent processes that are indistinguishable, this is how we do it. Q to the n divided by n factorial, which is the indistinguishability factor. So if we substitute in the partition function, and here I've got it in terms of kBt instead of beta, you get this expression. Okay, but our starting point that makes things a bit more convenient, if we look at the natural log of the partition function, now with log properties, this expression here, we could break those variables up. But I've written it out this way because it makes it more convenient when we actually start doing the partial derivatives. So for the pressure, it is the partial derivative of the partition function with respect to volume, and then we times it by kBt. So in the expression above, which terms do we have left? What goes away, which remains? So we get rid of everything that's not a function of the volume.
Pretty much everything except the whole right-hand term.
Only the very last one. So we have kBt. And so what is the partial derivative of this term here with respect to volume?
1 over v, I think.
Yep. Well, it's n times 1 over v. We rearrange this expression. We get PV equals K B T times n. Or we could write PV is equal to N R T, rather N A R T. No, sorry, not N A, sorry, N, in terms of units. Right, same form, the only difference is that in one case we're keeping track of the number of particles, the other one we're keeping track of the number of moles, which is still a unit of, it's just a counting unit. So we're just scaling them by Avogadro's number.
I know everything previously stands for how it worked out to that.
Yeah. Good thing it works out. Right, so remember, StatMech, the whole goal of StatMech was to reconcile atomic properties with classical thermo. So in order to pass any sort of muster, you had to be able to predict all of the classical properties and then contribute something else in addition. This is the most fun one. Internal energy we've already done, but I'll just write it out again. Is 3/2 n kBt. C sub v is just equal to du dt. Right, change internal energy with respect to temperature. Right, we talked about these ones at length already. The Helmholtz energy. This is actually a bit more complicated to calculate. It's a bit counterintuitive. This is the easiest equation to evaluate. But since we don't get to get rid of anything, right, because we're not taking the partial with respect to temperature or volume, and we don't get to cancel out half the terms, so we actually have to keep everything hanging around for a little bit. So all I've done is I've substituted the partition function into the equation for A, rather the single particle partition function. So this term here, we don't really have to do much manipulating. It's just an algebraic substitution of the single particle partition function. But we have to figure out a way to estimate the factorial of a very, very large number, right? Because this n could be exceptionally high. So what we use is something called Stirling's approximation. Stirling's approximation is typically written like this, rather approximate. But using log properties, we can write it slightly differently. Whereas natural log of E is just 1. So we can write that the Helmholtz energy and this I'm leaving the substitution for the partition function out. Okay. Now for the entropy, we're going to cheat a little bit, and we know that S is just equal to minus dA dt. So we're just going to take the partial derivative of that last expression with respect to temperature. Now remember, there's temperature dependency within the partition function, so we're skipping over the math, not showing it, but we have entropy now. And then lastly, the chemical potential. Again, skipping over the math.
Is that the unit with 5 over 2?
Correct, yep, 5 over 2. And internal energy. Okay, so what we've done. For the chemical potential, that one there. Sorry. Put brackets around it. Okay, so what we've done is we've taken the properties of how a single particle behaves. We scaled it up to a collection of particles. In this case here, this is Q. This is big Q. We calculated the internal energy of the system. in which case this was just e to the I probability. Right, it was just a weighted average of the energy of the system. The path that we took now was to then take that internal energy, manipulate it in a way that we're comfortable with using classical thermodynamics. Right? Right, the combined first and second law of thermodynamics, no matter what strategy we take, we still can't violate this law. So we can still rely on it. And then from there, we developed relationships for S, A, P, chemical potential. Did I miss any others? I think that's what we did, yeah. So where do we go from here?
Atomic gases.
That'll be a soon step. The next step actually we'll take is other potential, other ensembles. This is the next thing we're going to cover. Then we can make the individual molecules more complex. Diatomic, polyatomic, expand from there. Then we start talking about interacting gas systems, low density systems. This is essentially where the virial equation of state came from. So analytically, it gets very, very complex to do calculations on anything other than a moderate density gas. Analytically, it's exceptionally complex to try and accomplish something like a liquid behavior. The easiest thing that you can really kind of feasibly get your hand on is maybe like a hard sphere fluid, something that's a very simple, weakly interacting material. But by the end of class, and if we can get there, I'm hoping we can, last year we made it through talking about scattering theory and how you learn about atomic positions from experiments. And I'm hoping, if we can get through this, to actually have everyone run some MD simulations themselves on a simple software package and sort of generate radial distribution functions, properties, and things like that. But the same general approach that we walked through with the ideal gas is the same approach that we will do so with all the other ones. How does a single molecule behave? How would we expect it to behave in a collection? Is there interactions? Is there not interactions? With the ensemble that we're working in, how can we calculate macroscopic thermodynamic properties? So what we've done right now is we've worked through all of the functions for the canonical partition function. Those are going to stay the same no matter what. What's going to change when we add complexity is the partition functions themselves. Right? So now we have one tool that allows us to calculate the properties we want, another tool that allows us to change the properties of the molecules. And so with those two effects, we can do a lot of different things. So of course, with a diatomic gas molecule, we have vibrations and rotations. So now we have to find a way to categorize how energy is stored in bond vibrations and how energy is stored in molecular rotations. So of those two, rotations are actually the lower energy state. Vibrations are relatively high energy, so typically they don't get activated until you're several hundred degrees Kelvin, like 600, 700, 800 degrees Kelvin. But different gas molecules will have their bond vibrations activated at different conditions or temperatures, which is why they're all going to have slightly different heat capacity shapes as a function of the temperature as well. Okay, any questions? All right. Hopefully see you all at the seminar.